Hi boys and girls, welcome to your next lesson on atoms and radiation. From your fact book you'll need this information on atoms and radiation, and by the end of the session you'll understand and know and be able to recognize the three types of ionizing radiation, and you'll also be familiar with the equations for the ionizing radiation for two of them. So let's make a start then. What three subatomic particles are found in an atom? Give the charge and the mass for each of these subatomic particles. Describe J.J. Thomson's plum pudding model. When Rutherford did his experiment, the gold foil one, what three observations did he find? And what did each observation tell him about the structure of an atom? What conclusions did he draw? What is an ion? How is it created? And finally, what does the mass number of an element tell you? Pause the video, have a go at these questions. Answers are coming up next. So, three subatomic particles are protons, neutrons, electrons. The charge of them, +1 for neutrons, for a proton, Neutrons are neutral, 0, electrons are -1 charge. The mass for the proton and neutron, they're both relative mass of 1. Electron is almost 0. We say it's almost 0. Its mass is about 1/2000, that of a neutron and proton. J.J. Thomson's model was a sphere of positive charge with negative electrons dotted throughout it, a bit like raisins dotted throughout a pudding. Rutherford's three observations were that most alpha particles went straight through the gold atom, some were deflected off course, and very, very few alpha particles bounced right back. What were his conclusions? That when the alpha particles went straight through, that told him the atom is mostly empty space. When the alpha particles deflected, that told him the positive charge must be concentrated, because the alpha particles were also positive charge, so they repelled with the positive charge that was concentrated. And when they bounced back, this told him there must be a tiny, tiny dense nucleus that they're hitting and bouncing back from. Ion is a charged particle. It's created when an atom loses or gains electrons. And the mass number of an element tells you how many protons and neutrons there are in the nucleus of an atom. Let's start with nuclear radiation then. In the radiation topic, we'll be focusing on the nuclei. So when we talk about this, we're talking a lot about the nuclei, which is the plural of nucleus of an atom, rather than the whole atom itself. It's important to note that a radioactive substance has atoms that have unstable nuclei. They might have too many protons or too many neutrons, or the ratio of protons to neutrons might not be stable. These unstable nuclei try to become stable by emitting radiation. And this radiation could be tiny particles, or it could be excess energy. This process is called radioactive decay. Could you pause the video here and copy this information down, please? So here's a diagram showing, or an animation, showing radioactive decay happening. So we've got an unstable nucleus. The unstable nucleus then either releases an electromagnetic wave as energy, or it could release a particle of radiation. And the whole point of this is that the nucleus, which is unstable, wants to become more stable. It's important to know that radioactive decay is random. We don't know when it's going to happen exactly. We can't time it. It doesn't happen every 3 seconds or every 5 months. It's random. But it's also continuous. What that means is it will keep happening until all of the nuclei, unstable nuclei, have decayed and become stable. So it's a continuous process, but when exactly one atom in that substance decays, that's a random process. We don't exactly know then. Pause the video here and just copy the 2 bullet points down, please. Now there are 3 main types of radiation we'll be looking at: alpha, beta, and gamma. There is a third one called neutron emission. And neutron emission is where the energy allows a neutron to be emitted out of the nucleus. for your AQA GCSE, that is not something that you'll be going into in detail, so I've not really talked about that. But it's good to know that there is a fourth one called neutron emission. The three main ones we're looking at are alpha, beta, and gamma. These three are called ionizing radiation. And the reason is, when they hit an atom, so when this radiation shoots out of an unstable nucleus and it hits and collides with another atom, it can knock out the electrons from the orbit of that atom. We've learned from last lesson, when electrons are lost or gained, the atom turns into a charged ion. That's why it's called ionizing radiation. You might want to pause the video and get this information down. Now let's go through each of these three ionizing radiations in detail. First one is alpha particle. Alpha particle is made up of 2 protons and 2 neutrons. Now that structure is very important to know. 2 protons and 2 neutrons together makes an alpha particle. And this structure of 2 protons and 2 neutrons is very similar, or it's about the same, as a helium nucleus. The nucleus, the center part of a helium atom. So sometimes an alpha particle is referred to as a helium nucleus. It has a charge of +2 simply because it's got 2 protons in it. The 2 neutrons have no charge, but the 2 protons together in that particle give the alpha particle a charge of +2. And it has a mass of 4. Remember, each proton and each neutron has a mass of 1. There are 2 protons and 2 neutrons. Together, the particle has a mass of 4. This means that when an unstable nucleus loses those 2 protons and 2 neutrons, it releases an alpha particle. And here's an animation of this happening. So here's an unstable nucleus. The nucleus releases an alpha particle, 2 protons, 2 neutrons, which then forms a new nucleus. Because it's lost its 2 protons and its 2 neutrons, the atom changes into a new element. Remember, proton number tells you, or atomic number, tells you which element it is. This unstable nucleus has lost protons, so it's now turned into a new nucleus. Pause the video here and copy this information down, please. A beta particle. Beta particle is a fast-moving, high-energy electron. It's a single electron. It is negatively charged. We know that from our previous lesson. And we also know that electrons have almost zero mass, 1/2000. So a beta particle, being a single electron, has the same properties as a single electron. How is it made? Well, when an atom's nucleus decays with beta decay, a neutron first splits into a proton and an electron. It's a bit of a weird thing, this one. So we have a nucleus with the neutrons obviously inside there. One of those neutrons, if it's got too many neutrons, one of those neutrons splits and becomes into a proton and an electron together. The proton stays in the nucleus, but the high energy electron is then emitted, which means given out, as a beta particle. So here's your unstable nucleus. It's got too many neutrons. So we'll notice here that one of those neutrons, which is flashed there, if you quote that, there it is again, one of those neutrons, which is flashing there, has now split and become a proton and electron together. So I'll just rewind that there. It's split and become a proton and electron together. That electron doesn't belong in the nucleus, so it's shot out, and we call that a beta particle. The proton stays in the nucleus. Now we've got an extra proton as such. Because we've got an extra proton, the new nucleus is a new element. Pause the video, copy this information down, please. Gamma wave radiation. Important to know, gamma radiation is not a particle. Alpha and beta are both particles. Gamma is not a particle. It's a form of electromagnetic wave energy. When an unstable nucleus decays into a more stable nucleus, sometimes we get some excess energy that's left over. So the stable nucleus might still have some excess energy there. That energy is released as gamma radiation. So gamma radiation usually happens and is associated with alpha and beta first happening, and then the excess energy is released as gamma radiation. It's not a particle, so it has no mass. It's not a particle, so it's not charged. Gamma wave radiation has no mass and no charge. Here's your unstable nucleus, turned into a new nucleus, in this case by alpha decay, got 2 protons, 2 neutrons. Excess energy in the new nucleus is then released as gamma radiation. No change to the number of protons, no new element is made. Pause the video and copy this information, please. So here's your chance. I'd like you to copy this table out, and from the previous slides, from the previous things, go back if you need to. Please fill in this table. You should have got something like this. Compare your table to this information and correct any mistakes that you may have made. If you got them all right, brilliant. Right, moving on to nuclear equations. So, let's start with alpha decay first. We know from the periodic table, and I'm going to give you a generic equation first, so we'll refer to the elements as X and Y. We've got X as an element, and we know from the periodic table it has a mass number, A, and an atomic number, P. Atomic number is number of protons. When alpha decay happens, element X atom turns into Y. The mass number reduces by 4 because we've lost 2 protons and 2 neutrons. So we've reduced the mass number by 4. We also decrease the atomic number by 2 because an alpha particle is 2 protons, 2 neutrons. It's lost 2 protons. And we refer to the alpha particle as a helium nucleus, He42. And here's an example. Americium 24195 turns into a new element. Its mass number reduces by 4. Its atomic number reduces by 2. And there's your alpha particle. Please copy this information down. Next one, beta decay. Again, let's start with a generic one. X is your element. A is your mass number. B is the atomic number for that X element. Turns into a new element. In this case, the mass number stays the same because the neutron turns into a proton. So the mass has not changed. Neutron and protons have the same mass. However, because a neutron is turned into a proton, we've gained 1 proton as such. And we refer to the beta particle as E0-1. Here's an example of this happening. The mass number is staying the same. The proton number, atomic number, goes up by 1, and there is your particle. Please copy this information down for the beta decay. Nuclear equations for gamma. Could we have a gamma radiation equation? No, because gamma radiation is a wave, it's not a particle. It has no charge, no mass, no effect on the nucleus. There is nothing for us to write an equation for gamma. There are no equations for gamma. Pause the video. I'd like you to practice having a go at these equations for alpha and beta. First 2 are done for you. Please complete 3 through to 12. These are the answers you should have got. Compare your answers to these. Please correct any mistakes. And even if you didn't get full marks, that's absolutely fine. You've given it a go, and I'm really appreciative of that. So in the lesson, we've gone through what the 3 types of ionizing radiation are, and we've explained how to have a go at nuclear equations for alpha and beta. So to end, here is an exam-style question. Please have a go at this. Pause the video. I'd like you to spend about 10 minutes on this. And here's the mark scheme for you to answer, for you to mark your answers. I hope you guys are well. Take care, and we'll see you on the next lesson. Thank you very much. Bye, guys.